Webb pointed at a quiet patch of sky. Then a galaxy appeared that, by every textbook, should not be there. It is called the Big Wheel, a spiral 5 times the mass of the Milky Way, spinning as fast as the largest disks in today's universe. And it existed when the cosmos was barely 2 billion years old. Galaxies like that are supposed to take almost the full age of the universe to assemble. This one didn't wait. We will follow what Webb actually saw. The mature spiral that grew up early. The crowded neighborhood feeding it. The red dots no model predicted. The clusters that arrived too soon. And the slow, serious crack opening in the standard story of the cosmos. If this kind of deep sky reporting holds your attention, hit subscribe before we go further. You will want to be here for what comes near the end. The numbers are real, the tension is real, and the quiet question underneath all of it is getting harder to avoid. Take a breath. We start at the edge of the deep field. A postdoc at the University of Milano Bicocca was scanning Webb data for something else entirely, when a smudge in the corner of his field caught his eye. He almost ignored it. It looked like a normal spiral galaxy, the kind we see drifting through the modern universe. It looked too normal. That was the problem. The patch of sky he was studying sits more than 12 billion light years away. Light from that region left its source when the universe was barely 2 billion years old. Whatever was there should have been small, lumpy, half-formed, a cosmic toddler. What he was looking at was a fully grown adult. He assumed at first that the spiral was a foreground intruder, a nearby galaxy photobombing his image from billions of years closer to home. He set it aside and kept working. Then the team ran the spectroscopy. The light from that smudge had been stretched and reddened by the expansion of space itself, and the amount of stretching gave them the distance directly. There was no mistake. The spiral really was sitting deep inside the early universe, where nothing like it was supposed to exist yet. That was the moment a quiet science paper turned into a problem. Webb sees in infrared. That matters here, because the most ancient light reaching us has been pulled into longer and longer wavelengths over billions of years of cosmic expansion. By the time it arrives at Earth, it is invisible to optical telescopes. Hubble could glimpse the brightest of these distant objects, but only as faint blurs. Webb resolves them. It pulls them into focus. It hands astronomers something Hubble could never give them: the actual shape of a galaxy from when the universe was young. The shape it handed them this time was a spiral. A wide, structured, rotating disk with arms. A galaxy roughly 5 times more massive than the Milky Way, stretching across about 100,000 light years, spinning with the ordered grace of a fully developed system. The team named it the Big Wheel, partly for its size, partly for the speed of its rotation. Here is why that single image matters. Standard cosmology has a story for how galaxies grow up. Small clumps form first, they smash together, they merge over billions of years. Eventually, after a long and violent childhood, some of them settle into smooth, rotating disks. This is the slow path. This is the only path the models really allow. A spiral this large, this calm, this organized, in a universe still in its early years, breaks the timeline. There was not enough time for the slow path. The team that confirmed it published in Nature Astronomy in March of last year. The reaction inside astronomy was not panic. It was the quieter, more uncomfortable reaction. The kind scientists have when something fits no current explanation and cannot be dismissed as a glitch. The image was real. The distance was confirmed. The galaxy was mature. The universe at that moment was not. That fingerprint in the deep field opened a question the field is still trying to answer. Because if one impossible spiral is hiding in a single patch of sky, the obvious next question is how many more Webb is about to find, and what those discoveries say about everything we thought we understood about the beginning. Picture a city seen from above. Streets in clean radiating curves, lights tracing the outline of structure. Order on a scale you can feel before you can measure it. Now picture that city at full size, full population, full complexity, built in a landscape that according to every map should still be wilderness. That is what Big Wheel looks like inside its own era. Most galaxies from the early universe show up in Webb's images as small, irregular knots. Clumpy, asymmetric, smeared with the violence of recent collisions and bursts of star formation. They look like they are still being assembled. Big Wheel does not look like that. It shows two clean spiral arms wrapping around a bright central core. The disk is flat. The structure is symmetric. It carries the visual signature of a galaxy that has been quietly rotating for a very long time. The numbers behind the image are heavier than the image itself. Webb's spectroscopy measured the speed of stars at different points across the disk. The rotation curve, as astronomers call it, climbs outward and then flattens. Exactly the pattern seen in the largest mature spirals around us today. The maximum rotation speed reaches several hundred miles per second. That is comparable to the fastest disks in the modern universe. Big Wheel is not a small early galaxy that happened to look organized. It is genuinely huge, genuinely fast, and genuinely structured, and it had reached that state long before such a state was supposed to be possible. The team's measurement of its mass is what really tightens the screw. Roughly 5 times the Milky Way. That much stellar mass at that age means star formation was running at a furious pace for a very long stretch of cosmic time, faster than current models predict for a typical galaxy in that environment. Some kind of accelerator was in play. The slow merge and assemble path was not the only thing happening here. Here is the part that should land. Our galaxy, the Milky Way, is roughly 13 billion years old, give or take. It needed almost the full lifetime of the universe to reach its current size and shape. Big Wheel reached a size 5 times greater in less than a sixth of that time. Whatever happened there happened on a clock that nothing in the standard picture quite explains. The team has a working idea, though they are careful with it. Big Wheel sits inside a region of space crowded with other galaxies and hot streams of inflowing gas. The denser environment may have funneled material into the disk in a smooth, organized, rotating flow instead of through a violent series of mergers. Smooth feeding, in theory, can let a galaxy grow large without tearing itself apart. The disk would survive. The arms would form. The structure would hold. That idea fits the data. It does not fully resolve the puzzle. because even with optimal conditions, the speed of growth needed to produce Big Wheel pushes the limits of what current cosmology allows. The galaxy is real. The age is locked in. The mass is measured. And the universe has a deadline problem. Before we widen the lens, there is one more thing worth understanding. The way Webb knew, with confidence, that this galaxy actually belonged to the deep past. That measurement is the entire foundation of everything that follows. The whole story rests on one number. Get the number wrong, and the impossible galaxy collapses into an ordinary nearby one. Get it right, and the timeline breaks. That number is called the redshift. The universe is expanding. Space itself is stretching. Slowly. In every direction. All the time. When light travels through stretching space, its wavelengths get pulled longer along the way. Shorter wavelengths drift toward longer ones. Blue creeps toward red. Red creeps toward infrared. The further the light has traveled, the more its wavelengths have been stretched. The amount of that stretch is the redshift, and astronomers measure it with extreme precision. Here is the trick. Atoms emit light at exact, known wavelengths. Hydrogen has a fingerprint. Oxygen has a fingerprint. Iron has a fingerprint. These fingerprints are universal. They do not change. So when Webb collects light from a distant galaxy and breaks it apart with a spectrograph, the team can spot the fingerprints inside the spectrum. They know exactly where those lines should sit. They measure where they actually sit. The shift between the two gives them the distance. For Big Wheel, the redshift came in at about 3.25. That value placed the galaxy roughly 12 billion light-years away, in an era when the universe was only about 15% of its current age. The fingerprint matched. The shift was clean. The case was closed. This is why the discovery cannot be brushed off as a misidentified foreground galaxy. Webb did not just take a pretty picture. It read the chemistry of the light itself. Spectroscopy is the measurement that turns guesses into facts. Here is the wider point. Almost everything Webb has changed about our understanding of the early universe rests on this same kind of measurement. The little red dots, the supermassive black holes from before they were supposed to exist, the mature, dust-rich galaxies seen barely after the cosmic dawn. Every one of those discoveries depends on a clean spectroscopic redshift. Every one of them only counts as a real puzzle once the distance is locked in. The instrument doing most of this work is called the near-infrared spectrograph. It is mounted on Webb and designed to pull apart light from up to 100 objects at the same time. It can resolve shifts in wavelength so tiny that they would vanish in the noise of older telescopes. That sensitivity is what allows the team to spot a hydrogen line buried under 12 billion years of cosmic expansion, and confirm, with confidence, where in time the galaxy actually sits. Translate that into something physical. The light Big Wheel emitted left its source while the first multicellular life on Earth was still well over 8 billion years away from existing. That light traveled through silent, stretching space for longer than our entire planet has been here. It reached Webb in deep orbit, slipped through its mirror, hit the spectrograph, and surrendered its secret. The galaxy was old, and the universe at the time was young, and the math could not be pushed any other way. The number stands, the distance stands, the puzzle stands. Now the next question moves into focus. If the galaxy is real and the age is locked, what does that age actually mean? How young was the universe really, when this giant spiral was already turning? A galaxy is not just a pile of stars. It is a structure with a history. It has a birth date, a youth, a long stretch of slow assembly, and eventually, if conditions allow, an organized shape. That history takes time. The whole question of whether Big Wheel breaks the rules comes down to whether the universe had given it enough of that time. The standard age of the universe is about 13.8 billion years. That number is built from many independent measurements, and it has held up under serious testing. The cosmic microwave background, the leftover glow from the early cosmos, gives us one estimate. The expansion rate gives another. The aging of the oldest stars gives a third. They agree closely enough that astronomers treat the figure as solid. Big Wheel's light tells us it existed roughly 2 billion years after that beginning. 2 billion years sounds long. For Earth, 2 billion years is the gap between the appearance of the first complex cells and the rise of the dinosaurs. It is a vast stretch of biological time. For a galaxy, though, 2 billion years is barely childhood. The standard story says galaxies need most of the universe's age to reach the size and structure of the Milky Way. Big Wheel reached 5 times that size in less than a sixth of that span. To picture the gap, slow it down. Imagine a film of the cosmos, played from the first moments to today, compressed into one 24-hour day. The Big Bang lights up at midnight. The first stars flicker on around 4 in the morning. The Milky Way slowly assembles across most of the day. Earth forms in the late afternoon. Humans appear in the last few seconds before midnight. In that same compressed day, Big Wheel was already a fully formed giant by sunrise. That is the timeline problem in plain language. The universe at that moment had not yet finished its early phase. The cosmic web of dark matter was still organizing itself. The largest dark matter halos, the gravitational cradles inside which galaxies are supposed to grow, were still being built. Inside those cradles, gas was still cooling and falling inward. Stars were still forming in chaotic bursts. Mergers were still violent and frequent. The conditions for a calm, ordered, massive spiral were not supposed to be in place, and yet the spiral was there. The team that confirmed Big Wheel ran the math both ways. They asked how rare a galaxy this large would be in their patch of sky, given current models. The probability of finding one in their dataset came out below 2%. Not impossible, on paper, just unexpected enough to demand explanation. Then they asked what it would take to grow a galaxy of this mass within the available time. The conversion of gas into stars would have had to run far above the typical rate seen in the modern universe, sustained for hundreds of millions of years without interruption, inside a cradle that was already more massive than its peers. Every dial pushed near its maximum. Every stage of growth aligned without a single setback. The galaxy is the result of those dials being pushed. The question is whether the universe could really push them. That is the age problem. The galaxy is real. The clock is real. The mismatch is real. Spiral galaxies are not random. They are the product of a long, balanced argument between gravity and motion. To build one, the universe needs three things at once: a heavy disk of gas, a stable rotation, and enough quiet time for that rotation to organize the gas into arms. Each of those three is hard to produce in the early cosmos. All three at once was considered out of reach. Start with the gas. A galaxy disk needs a vast reservoir of cool hydrogen settled into a thin, rotating layer. Cool gas does not appear on demand. It has to fall inward from the surrounding cosmic web, lose energy, and settle into a flat plane. That cooling takes hundreds of millions of years. In the early universe, much of the gas was still hot and turbulent, freshly stirred by the violent first generations of stars. Settling that gas into a calm disk was a slow process by design. Now add rotation. A disk does not exist without spin. The angular momentum of a galaxy comes from the way matter flowed into its dark matter cradle from the surrounding cosmos. Early cradles received their gas in chaotic streams from many directions. Rotation had to emerge from the average of those flows, and the average took time to stabilize. Until it did, gas piled up in irregular clumps, not in ordered disks. Now add patience. Spiral arms are not painted onto a galaxy. They are density waves rolling through a stable rotating disk over many revolutions. A galaxy needs to spin many times for arms to develop and hold their shape. One full rotation of a Milky Way-sized disk takes roughly 250 million years. To build clean spiral structure, a galaxy needs several rotations free of major disruption. Mergers ruin that. Bursts of star formation ruin that. Active black holes at the center can ruin that. The early universe was a place where disruptions were the rule. That is the reason the textbook said mature spirals belonged to a later era. The first few billion years were supposed to be the assembly phase. Galaxies in that phase were expected to look like wreckage, lumpy, distorted, caught mid-merger. Webb was supposed to confirm that picture by finally showing it in clear infrared light. Webb did show the chaos. Most early galaxies it imaged are exactly as messy as the models predicted. The surprise is that the chaos is not the whole picture. Tucked among the clumps and the wrecks, Webb has resolved a small but real population of galaxies that do not match the assembly story at all. Disks, arms, symmetry, calm rotation. Big Wheel is the most extreme example, but it is part of a pattern, not an isolated freak. The pattern is what changes the conversation. One impossible spiral could be an outlier. A handful of impossible spirals, all confirmed by spectroscopy, all sitting at ages when they were not supposed to exist, suggests something about the universe's early years that the standard story missed. Something accelerated structure formation in at least some regions. Something fed disks fast enough to keep them whole. Something held the chaos at bay long enough for arms to form. The textbooks were not wrong about the chaos. They were incomplete about the order. The tool that confirmed this was a single measurement, made on a galaxy already known to be huge. A measurement so simple, so direct, that it left almost no room for argument. A rotation curve is the simplest honest portrait of a galaxy. It plots the speed of stars and gas at different distances from the center. The shape of that plot tells you almost everything about how mature the galaxy is. There is no way to fake it. Either the disk is rotating in an organized way, or it is not. Webb pointed its spectrograph at Big Wheel. The team measured the velocity of material on one side of the disk and on the other. Light from gas moving toward us was shifted slightly toward shorter wavelengths. Light from gas moving away was shifted toward longer ones. The pattern of those shifts, mapped across the face of the galaxy, traced the rotation directly. The plot they built came back with a shape that should not have appeared at that distance. The curve climbs steeply from the center outward, then flattens at a high speed and stays flat. That flat plateau is the signature of a fully developed rotating disk. It is what we see in the largest mature spirals around us today. It tells us that the galaxy's mass, including its dark matter halo, is distributed in a specific balanced way, and that the disk has been rotating in that balance for long enough to settle into it. The plateau speed they measured runs at several hundred miles per second. That is the rotational tier of the biggest disks in the present-day universe. It means Big Wheel is not just visually similar to a mature spiral, it is dynamically a mature spiral. The mass distribution, the rotation, the structural balance, all of it matches galaxies that have had 10 or 12 billion years to settle. Big Wheel had less than 2. There is a deeper layer to this measurement. Modern astronomers have a tool called the Tully-Fisher relation. It is an empirical link between a spiral galaxy's rotation speed and its total mass. Plot rotation against mass for spirals in our local universe, and the points fall on a clean line. The relation is one of the most reliable patterns in astronomy. It holds across galaxies of wildly different ages and environments. Big Wheel sits on that same line. That is what shocked the team. A galaxy from 12 billion years ago, growing inside an unfinished universe, obeys a relation built from galaxies in the modern cosmos. The same physics is in play. The same structural balance has already been reached. By every internal measurement, Big Wheel is a member of the mature spiral family, just observed billions of years earlier than any member of that family was supposed to exist. The implication is harder to dismiss than the image. A picture can be misread. A redshift can be argued over until the spectrum lands. A rotation curve sitting cleanly on the Tully-Fisher relation cannot be argued away. It is a fingerprint of dynamical maturity. The galaxy carries it. The era does not. This is the measurement that turned Big Wheel from a curiosity into a problem. Astronomers who specialize in galaxy formation read the rotation curve and understood the timeline issue immediately. The data was clean. The geometry was clean. The interpretation was nearly forced. A mature disk had appeared in a universe that was not supposed to be old enough to make one. The first instinct in any field, when something this strange shows up, is to ask whether it is alone. The team that found Big Wheel had a hunch it would not be. Another team, working on a different patch of sky, was already preparing to publish. The second discovery did not come from Italy. It came from India, from two researchers at the National Center for Radioastrophysics in Pune, sifting through Webb data the way prospectors sift through gravel. Rashi Jain and Yogesh Wadadkar were studying a different patch of the deep field. They were not hunting for impossible spirals. They found one anyway. They named it Alaknanda, after a Himalayan river that joins others to form the Ganges. The Hindi word for the Milky Way is Mandakini, which shares the same headwaters. The naming was a gesture, not an exaggeration. The galaxy really does look like ours. Two clean spiral arms wrap around a bright central bulge. The structure is symmetric, the kind astronomers call grand design. Most spirals in the modern universe are messier than this, with broken or irregular arms. Grand design spirals are the elegant exceptions. Alaknanda is one of them, and it existed when the universe was about 1.5 billion years old. That places it even earlier in cosmic time than Big Wheel. The light from Alaknanda left its source not long after the cosmic dawn. By the standard model, galaxies in that era should still be in their lumpy, chaotic, half-assembled phase. The famous Hubble Ultra Deep Field showed exactly that. A sky full of irregular blobs and forming clumps. Webb's deep images mostly confirm the pattern. Alaknanda breaks it. 2 arms, a bulge, order. A structure that looks like it has already been spinning for a long time, in a universe barely old enough to allow it. The team measured its star formation rate. Alaknanda is producing new stars at roughly 20 times the current rate of the Milky Way. That is a furious pace, sustained across the whole disk. It explains how the galaxy reached its mass so quickly, but it deepens the structural puzzle, not eases it. Star formation that intense usually disrupts disks. Bursts of new stars create powerful winds. Supernovae rip through the gas. The disk should be turbulent. The arms should be ragged. The arms are not ragged. The disk is not turbulent. Something is keeping the structure intact while the galaxy grows at top speed. The team's best guess, like the Big Wheel teams, points to the local environment. Alaknanda lies in a region of space behind a foreground galaxy cluster called Abell 2744, which acts as a natural lens that magnifies and clarifies the view. The cluster amplifies the light, but it does not invent the structure. The order in the disk is real. 2 galaxies, 2 teams, 2 different patches of sky, 2 different epochs of the early universe, both showing the same impossible signature. Mature spiral structure where mature spiral structure was not supposed to be. When 2 independent groups confirm the same kind of anomaly using different data, the field moves from surprise to attention. One discovery can be a fluke. 2 start to feel like a sample. And a sample is the beginning of a population. A population of mature early spirals would mean the universe knew how to build organized galaxies long before the textbook said it should. The next step is figuring out where these galaxies live. Because if the environment is the key, then the early cosmos had favored neighborhoods. Crowded ones, loud ones, places where growth ran far ahead of the rest. Big Wheel sat in exactly that kind of neighborhood. A galaxy does not grow alone. The space around it matters. Whether it sits in a quiet, sparsely populated stretch of cosmos, or inside a dense, busy region changes everything about how it forms, how fast it grows, and how stable it remains. Big Wheel does not sit in a quiet stretch. It sits inside a region of the early universe where galaxies are packed roughly 10 times more densely than the cosmic average. That figure carries weight. The early cosmos was not uniform. Matter clumped along filaments of dark matter, like dew gathering on threads of a web. Some filaments were sparse, others ran thick with material, with many young galaxies threaded along their length. The thick regions are where the action concentrated. Big Wheel grew inside one of those thick zones. Density at this level changes the supply chain of a galaxy. In a sparse region, gas drifts in slowly, in chaotic streams from random directions. Growth is irregular. Mergers are violent and rare. In a crowded region, the surrounding cosmic web pumps gas inward in steady, organized flows. The galaxy is being fed continuously from many filaments at once, and the flows tend to align with the rotation already present in the disk. Smooth feeding, aligned spin. The conditions a forming spiral actually needs. The team that confirmed Big Wheel sees this as the most plausible explanation for how it grew so large, without tearing itself apart. Inside its dense neighborhood, the cosmic web kept handing it cool gas in a single coherent direction, year after year, for a long stretch of cosmic time. The disk drank, expanded, rotated faster, and never had to reset. There were probably mergers. The dense environment guarantees them. But the mergers were minor compared with the steady inflow, and the disk absorbed them without losing its overall shape. That picture explains the size. It does not fully explain the speed. Even with optimal feeding, current models struggle to grow a galaxy 5 times the mass of the Milky Way in less than 2 billion years. The gas has to convert to stars at a sustained efficiency that pushes the upper limits of what physics allows. Some of the inflow has to bypass the usual feedback losses, where supernovae and stellar winds blow material back out of the disk. The dark matter cradle around the galaxy has to be unusually massive for its era, sitting at the high end of what the early universe was supposed to produce. Every dial has to be near maximum, and every dial has to stay there. A few astronomers have started using a quieter word for places like this: privileged. Not in any cosmic fairness sense, in a statistical one. Some patches of the early universe were privileged with deeper cradles, denser webs, smoother inflow, and more time without disruption. Galaxies inside those patches grew at rates that are rare across the sky but real where they happened. Big Wheel is one of those galaxies. Alaknanda is probably another. If that is the right reading, then the early universe was not uniformly slow. It was patchy. Most regions matched the textbook. A small minority ran far ahead. Webb is now sensitive enough to see the privileged regions for the first time, and what it sees there does not look like the early universe we were taught. Inside Big Wheel's neighborhood, there is one more piece worth noticing. A monster sits there, feeding at the same time as the disk. And what it is doing changes the picture again. Near Big Wheel, in the same crowded patch of early space, sits a quasar. A quasar is what happens when a supermassive black hole feeds at full throttle. Gas spirals down toward it, gets crushed and superheated, and blazes outward as one of the brightest sustained sources of light in the universe. A single quasar can outshine the entire galaxy that hosts it. Quasars are visible across nearly the full span of cosmic history because their light cut through the dark like a flare. The quasar near Big Wheel was already known. It is what drew Webb to that patch of sky in the first place. The team's original goal was to study the quasar's surroundings. Big Wheel showed up as an unintended bonus. Here is the connection that matters. Quasars in the early universe are themselves a puzzle. They are signposts of supermassive black holes that, by standard models, should not yet have grown to their observed sizes. The math will hit harder in a later chapter, but the short version is this. Black holes of the scale powering early quasars need most of the universe's age to reach their masses. Many of them reach those masses far sooner. The quasars are the proof, glowing across the cosmos. So the patch of sky that hosts Big Wheel hosts both kinds of impossible object at the same time. A mature spiral that grew up too fast. A supermassive black hole that grew up too fast. In the same neighborhood, drawing on the same dense cosmic web. That coincidence is probably not a coincidence. Astronomers have long suspected that the most overdense regions of the early universe were where the largest objects assembled first. Heavy seeds, fast feeding, rapid growth across multiple categories of structure at once. A region that managed to produce a big wheel might also be the kind of region that produced a giant black hole nearby, simply because both rely on the same underlying conditions. Deep, dark matter cradles, steady gas inflow, dense surroundings, a privileged neighborhood for everything massive. There is a flip side too, and the team is careful with it. Quasars do not feed politely. They blast radiation and high-speed winds outward across enormous distances. Those winds can heat the gas in nearby galaxies, slow down star formation, and disrupt growing disks. A quasar this bright should, in principle, be a problem for any galaxy in its vicinity. Big Wheel does not look like it has been disrupted. Either the quasar's effects fell mostly in directions away from the spiral, or Big Wheel was massive enough by then to weather the storm without losing its disk. That is the sort of detail that does not resolve a puzzle, but sharpens it. The neighborhood was hostile and generous at the same time. It fed Big Wheel and lit a beacon nearby. The galaxy and the black hole are separate objects, but they are part of the same story. Both are markers of a region of the early universe where structure formation outran its own schedule. The quasar tells us we are not looking at a single fluke. We are looking at a region that produced multiple kinds of impossible things at once. Whatever accelerated growth in this part of the deep field was not picky about which kind of object it accelerated. That changes the question entirely. The pattern keeps widening. Astronomers have a phrase for what they have been seeing. They use it carefully, often in quotes. The impossible early galaxy problem. The phrase started showing up in serious literature within the first year of Webb's science operations. By now, it has become the shorthand for a growing collection of observations that, taken individually, can be argued with, but taken together, point in one direction. The collection includes Big Wheel, the giant mature spiral. It includes Alaknanda, the grand design spiral from even earlier. It includes a group of ultramassive galaxy candidates Webb spotted in its first deep fields, several of which appeared to carry stellar masses far higher than current models predicted for their epoch. It includes evidence of dust, heavy elements, and complex chemistry in galaxies barely old enough to have formed any of those things. It includes supermassive black holes with masses that, on the current clock, had nowhere near enough time to grow. Each of those discoveries is a separate paper. Each has its own caveats. Each can be defended or challenged on its own technical grounds. The pattern is what is hard to wave away. The standard model of cosmology, called lambda CDM, makes specific predictions about how fast structure can form. It predicts the size of dark matter cradles at each cosmic epoch, the typical mass of galaxies inside them, and the rough efficiency at which gas converts into stars. Those predictions are not loose. They are tied to the cosmic microwave background, to the observed expansion rate, to the distribution of galaxies in the modern universe. The model has been remarkably successful for decades. Webb has not broken the model, it has put weight on its joints. The clearest joint is what astronomers call stellar mass efficiency. To grow a galaxy of a given size in a given time, you need a certain fraction of the available gas to turn into stars. Standard models cap that fraction below about 20% for typical galaxies. Some Webb candidates appear to require efficiencies pushing toward 50%, in some cases higher. A few early estimates needed efficiencies above 100% to match the data, which is physically impossible. Better measurements pulled most of those candidates back into the realm of the possible. The remaining ones still sit in uncomfortable territory. The defense of the standard model goes something like this. Selection bias matters. We tend to find the brightest, biggest, most active galaxies first, because those are the easiest to spot. The early universe almost certainly hosted plenty of small, ordinary galaxies that match predictions. A few outliers near the top end of the mass distribution are not enough by themselves to break the model. A recent paper out of the University of California, Irvine, argued exactly this: that careful statistical treatment, combined with reasonable adjustments for measurement uncertainty, can explain most of the tension without invoking new physics. That defense holds partially. It does not erase the question. Selection bias can explain why we see so many massive galaxies early. It does not explain how the universe grew them at all. The galaxies are real. The masses are measured. The clock is the clock. The pattern is now too large to ignore and not yet large enough to overturn the model. Astronomy is sitting in the most uncomfortable position a science can sit in, watching the evidence accumulate, waiting to see which way the weight tips. Some of the strangest pieces in that accumulation do not look like galaxies at all. In Webb's first deep images, scattered across the field like stars on a dark beach, astronomers noticed something they could not place. Tiny red points of light. Compact. Bright. Stubbornly featureless. They did not match any known class of object. They did not appear in Hubble's data because Hubble could not see in this part of the infrared. Webb pulled them out of the dark for the first time. The team called them little red dots. The name stuck. For a while, the little red dots were dismissed as a curiosity. There were not many of them. They could be unusual galaxies, or maybe distant stars, or maybe artifacts. As Webb collected more data, the count grew. By the second year of operations, hundreds of little red dots had been catalogued, all of them sitting deep in the early universe, all of them strange in the same way. Their colors told one story, their shapes told another. The light from a little red dot is dominated by the deep red end of the infrared. That is partly because they are far away, and the universe's expansion has stretched their light into longer wavelengths. It is also because their intrinsic spectra carry a heavy red tilt, as if their light is being reddened by dense clouds of gas and dust around the source. They are not just distant, they are wrapped in something. Their shapes are the second puzzle. In Webb's images, little red dots are not extended. They are points, unresolved. That tells astronomers their light is coming from a region small enough that even Webb cannot pick it apart. Most galaxies, even at extreme distances, show some smear of structure. The dots show none. Whatever is making this light is concentrated in a region tighter than a typical early galaxy. That combination, small, red, deep in the early universe, wrapped in gas, does not fit any familiar object class. Some early papers proposed that the dots were small galaxies hosting unusually intense star formation. Others suggested they were active black holes hidden inside thick dust shrouds. A third idea, stranger than both, has been gaining ground. The third idea is that the dots are something nobody had named before. A new kind of object. One that does not exist in the modern universe. A team out of the University of Copenhagen published in Nature earlier this year, arguing that the little red dots are best explained as compact. Dense balls of hot gas powered not by ordinary star formation, but by a supermassive black hole at the center, feeding furiously through a thick envelope. Other groups have called these objects black hole stars. The name is informal, and the science behind it is still being debated. The core idea is that in the very earliest universe, before galaxies had time to settle into disks, gas could collapse directly into the central region of a forming halo and feed a young black hole inside a roiling envelope of plasma. From the outside, the whole structure would look like a single compact red point. Not quite a galaxy, not quite a star, a cosmic hybrid. The little red dots may be those hybrids, finally caught on camera. If that interpretation holds, the early universe had a phase nobody knew existed. A phase between primordial gas and modern galaxies. A phase Webb is mapping in real time. And inside that phase, something was already pulling matter into shapes that current cosmology has no clean place for. The black hole star idea sounds outrageous until you sit with the physics. Then, it stops sounding outrageous and starts sounding necessary. Here is the problem the idea is trying to solve. Webb sees supermassive black holes in the early universe with masses of tens of millions of solar masses, sometimes hundreds of millions, sitting inside galaxies that look barely formed. The black holes are too big for their hosts. They are too big for their age. Standard formation channels start a black hole as a stellar remnant, a leftover from the death of a massive star, with a few tens of times the mass of our home star. From there, the black hole grows by feeding on gas. Feeding has a speed limit, set by the radiation pressure of the infalling material. That limit is called the Eddington rate. At the Eddington rate, a black hole can roughly double its mass every 50 million years in optimal conditions. Run the math. Start with a stellar remnant black hole at the end of the cosmic dark ages. Feed it at the Eddington rate without interruption for the entire available time. It still cannot reach the masses Webb is seeing in the early universe. Not even close. Something has to bypass the slow path. The leading idea is called direct collapse. In specific early environments, a large cloud of gas collapses without first fragmenting into stars and forms a single enormous seed black hole with thousands or even hundreds of thousands of solar masses in one event. From a heavy seed like that, you can reach the observed masses inside the available time. The math closes. The catch is that direct collapse needs special conditions: hot gas, suppressed cooling, no earlier star formation in the same cloud. Such conditions are possible in the early universe, but they are not common. Direct collapse is supposed to be rare. The little red dots are giving astronomers a place to test the idea. If a black hole star is what a direct collapse seed looks like in its early feeding phase, then the dots are direct evidence that the heavy seed channel exists. The compact size matches a single deep gravitational well. The reddened spectrum matches a thick envelope of gas and dust around a feeding black hole. The brightness matches a feeding rate at or near the Eddington limit, sustained for a long stretch. Every feature lines up with a direct collapse seed in mid-meal. Several observational details strengthen the case. Some little red dots show broad emission lines in their spectra, the kind produced when gas is whipping around at thousands of miles per second near a central engine. That is a classic active black hole signature. Other dots show ratios of light at different wavelengths that match models of dense gas envelopes around hot accretion disks better than they match models of starbursting galaxies. The picture is not closed. Some little red dots may turn out to be compact starburst galaxies after all. The community is divided carefully, the way astronomers usually are when a new class of object first arrives. Here is the part that matters for the larger story. If even a fraction of the little red dots are direct collapse black hole seeds caught in the act of feeding, then the early universe was producing supermassive black holes at a much faster rate than the standard story allows. The pressure on cosmology gets heavier. The mass tension does not just live in galaxies, it lives in their central engines too. Webb is showing us that the early cosmos built large structures across multiple categories at the same time, and built them faster than any current model comfortably permits. The pattern has reached the heart of galaxies. Now it expands outward. A galaxy cluster is the heaviest single structure the universe builds. Hundreds of galaxies bound together by gravity, threaded with hot gas, anchored to a vast halo of dark matter. Clusters take a long time to form. They grow by repeated mergers across most of the universe's history. The largest clusters in the modern sky needed nearly the full age of the cosmos to reach their current mass. Then there is El Gordo, the fat one. El Gordo is the most massive galaxy cluster ever observed in the early universe. It was first identified more than a decade ago, before Webb, by other instruments. Webb did not discover it. Webb has helped sharpen the picture of just how strange it is. The cluster carries a total mass on the order of 3,000 trillion times the mass of our home star. It is a smash-up of two huge subclusters, caught mid-collision, racing toward each other at thousands of miles per second. That collision is happening at a redshift that places the cluster in the early universe, when the cosmos was less than half its current age. At that point, the standard model says no cluster should have grown that big yet. The dark matter cradles, needed to hold a structure of that mass, simply should not have had time to assemble. A peer-reviewed analysis published a couple of years ago put it bluntly. El Gordo, it argued, formed too early with too much mass and at a collision speed too high to be compatible with the standard model. The probability of finding such a cluster at that epoch in a lambda CDM universe is, depending on the assumptions, vanishingly small. Some statistical defenses bring the probability back into the realm of bad luck rather than impossibility. The defenses depend on careful choices. Choices like that are where the cracks in the model show up. Each individual case can be defended. The pattern of cases is the part that strains the seams. Here is why El Gordo matters for the Big Wheel story. Big Wheel is one mature object. The little red dots are point-like central engines. El Gordo is a full assembly of galaxies, hot gas, and dark matter, all of it bound together at a scale that should not exist yet. The same accelerated growth that produced Big Wheel and the early black holes appears to have produced cluster-scale structures too. The tension is not local to galaxies. It runs all the way up to the largest gravitationally bound objects in the universe. The cluster's collision adds a second layer of strangeness. The two subclusters are slamming into each other at a speed that, in current models, would be hard to reach in the time available. Building enough mass and enough relative velocity at the same time, that early in cosmic history, demands an unusually deep gravitational potential and an unusually long history of acceleration. Both are hard to deliver in the available window. Astronomers describe El Gordo carefully. They do not say it disproves cosmology. They say it is in tension with the model. Tension is the field's word for a measurement that does not fit cleanly, but cannot be dismissed. Several measurements are now in tension. They are not the same kind of tension. They live at different scales. A galaxy here, a black hole there, a cluster across the sky, but they share a direction. They all point toward early structure that grew faster than the slow path allows. Big Wheel grew too fast. The little red dots grew too fast. El Gordo grew too fast. The pattern is no longer about individual oddities. It is about the rate at which the universe built things, and whether our understanding of that rate needs serious revision. The next pressure point sits at the center of those overgrown structures. The mass tension at the center of galaxies is, in some ways, the cleanest version of the whole problem. Black holes obey simple rules. They have a maximum feeding rate. They have a clear timeline. The math is unforgiving. Webb keeps finding black holes that broke the math. The most extreme cases sit at redshifts above 7, meaning we are seeing them as they existed when the universe was less than 800 million years old. Their masses run from tens of millions to, in a few cases, near 100 billion times the mass of our home star. A few are bigger than the central black hole of the Milky Way, which has had 13 billion years to grow. Webb is seeing comparable or larger black holes that had less than 1 billion years to do it. Let the gap settle for a moment. Our central black hole is roughly 4 million solar masses. Some of these early black holes are tens of thousands of times more massive, in less than 1/10 the time. The simple slow growth math, starting from stellar remnant seeds and feeding at the Eddington limit without interruption, cannot reach those numbers. Not by a factor of 10, not by a factor of 100. That is why the direct collapse idea has gained traction. Heavy seeds, formed early through unusual conditions, can shorten the path. Even with heavy seeds, though, the largest early black holes still require near continuous feeding for almost the entire available window. No quiet periods, no major disruptions. A long, hungry meal across hundreds of millions of years. Some astronomers have explored a more aggressive answer. Super Eddington feeding. The Eddington limit assumes that radiation pressure from infalling matter pushes back against the inflow, capping the feeding rate. In real complex environments, parts of the radiation can escape sideways through low-density channels, while gas continues to fall through denser ones. In that geometry, a black hole could feed faster than the textbook limit, at least in short bursts. If super Eddington phases happened often enough in the early universe, they could explain some of the mass tension without invoking new physics. The catch is that super Eddington feeding is messy. It would produce strong outflows. It would interact powerfully with the surrounding gas. Webb has seen some hints of these signatures in early black holes, but the picture is not clean. The community is studying it. There are stranger ideas in circulation too. Primordial black holes, formed in the first fractions of a second after the Big Bang, carrying built-in mass from cosmic conditions long gone. If primordial black holes existed, they could have started the growth process before stars even formed, giving the early universe a head start on its largest engines. The idea is fringe, but not absurd. It is consistent with several observational hints, and it is taken seriously by a minority of cosmologists. Webb has not confirmed it. Webb has not ruled it out. What Webb has done is sharpen the question. The black holes are real. The masses are measured. The redshifts are confirmed. Whatever channel produced them ran fast and ran early, and the standard slow path does not close the gap on its own. This is the most uncomfortable kind of discovery. It does not point at one clean answer. It points at the absence of a clean answer. A piece of physics is missing somewhere, either in the seeding, or in the feeding, or in the timing, or the underlying cosmology that sets the clock. Whichever piece is missing, the strain is real, and it is showing up in the same place the galaxy strain shows up. The center of the early universe was building heavy things on a schedule that no current model fully owns. The next strain shows up in the raw material those heavy things were built from. Galaxies are built from gas. Specifically, cool, dense, neutral hydrogen falling into dark matter cradles, settling into rotating reservoirs, and converting into stars. To grow a galaxy fast, you need a generous, sustained, organized supply of that gas. To grow many galaxies fast, you need that supply across large regions of the early universe. The question Webb is forcing is whether the early universe actually had it. In the standard story, the first cool gas is hard to come by. After the Big Bang, the cosmos was a uniform plasma. As it expanded, it cooled, and electrons and protons combined into neutral hydrogen. Then came a long, dark phase before the first stars. When stars finally lit it up, they ionized the surrounding gas again, breaking it back into charged particles. That re-ionized gas is hot, fast, and resistant to forming new stars. Cooling it back down into a state where it can fall into a galaxy and form a disk takes time. So the early universe had a chicken and egg problem. To grow big galaxies fast, you need a lot of cool gas. To get a lot of cool gas, you need conditions that the first generations of stars actively work against. Webb is now showing us regions of the early universe where that problem appears to have been solved, somehow, on a fast timeline. Big Wheel's neighborhood is one. Cool gas was clearly being delivered into the disk in steady, organized streams, fast enough to feed 5 Milky Ways worth of stars in less than 2 billion years. The little red dots, if they are direct collapse black hole seeds, also imply dense pockets of cool gas, settled enough to collapse all at once. El Gordo's enormous gas envelope, hot and X-ray bright, implies a deep dark matter cradle that was already pulling in vast reservoirs at an early stage. Each case demands a generous gas supply. The pattern demands that the supply was not exotic or rare in the right neighborhoods. There are mechanisms that can deliver the supply. The cosmic web channels gas along its filaments, and the densest filaments concentrate gas at their intersections. A galaxy at one of those intersections receives gas from multiple directions at once. If the filaments are aligned and the inflow is smooth, the gas arrives cool and organized. Some early galaxies seem to have grown precisely in those locations. Webb's images of dense early environments often show multiple galaxies threaded along visible filaments with gas flowing between them. That picture works in principle. The trouble is the rate. To deliver enough gas to grow Big Wheel and similar objects within their windows, the cosmic web's flows had to be running at the high end of what models allow. Some current simulations cannot quite produce the rates needed. They produce smaller galaxies on the same timeline. They reach Big Wheel-sized galaxies later. The gap is not nothing. A few astronomers have started to wonder whether the early universe held more cool gas than the standard story allows, perhaps through cooling channels that current models underrepresent. Molecular hydrogen cooling, for example, can be efficient under specific conditions, especially if dust forms early and acts as a coolant. If dust appeared in the early universe faster than expected, cooling speeds up, and gas reservoirs can settle and fall into galaxies sooner. That brings us neatly to another piece of the puzzle. Dust is not just incidental in this story. Dust is one of the heavy chemical signatures that early galaxies should not have had time to make. And Webb is finding dust in places where dust should not yet exist. Dust is the universe's record of death. It is made of heavy elements forged inside stars and scattered across space when those stars explode. Carbon, oxygen, silicon, iron. Every grain of dust in space is a fragment of a stellar life cycle that already ended. To have a lot of dust, you need a lot of stars to have lived and died first. Webb keeps finding heavy dust in galaxies that, on the standard clock, should be too young to host more than 1 or 2 generations of stars. The first generation of stars is called Population 3. These were the original stars formed from primordial hydrogen and helium, with almost no heavier elements. They had no dust to be made from, and they had to make it themselves by burning through their nuclear fuel and exploding as supernovae. That process takes time. A massive star can live for only a few million years before it explodes, which sounds short, but the chain from formation to explosion to cooling debris to dust grains to redistribution into the galaxy involves many steps. The whole cycle does not finish overnight. Webb is showing us galaxies less than 1 billion years after the Big Bang that already contain measurable quantities of heavy dust. Some early universe galaxies show carbon emission lines so strong that they imply complex chemistry was already running at full pace. Others show oxygen and silicon at levels that would normally require many cycles of star birth and death to produce. The early universe was supposed to be chemically simple. Webb is finding it chemically advanced. This is not a single galaxy's anomaly. It is showing up across the population of early galaxies. The community has a name for it now: early dust enrichment. The phrase is technical. The implication is not subtle. The chemical clock of the early universe ran faster than expected. There are possible explanations. One is that the first generations of stars were unusually massive and short-lived, dying in great numbers very quickly and seeding the surrounding gas with heavy elements at top speed. That would compress the dust-building timeline. Another is that early dust was made through pathways we have not fully modeled, perhaps through rapid grain growth in dense regions, accelerating the buildup of heavy material once seed grains existed. A third is that some early galaxies inherited heavy elements from earlier sources we have not yet identified, perhaps from primordial black hole environments or from the violent deaths of the first ultramassive stars. None of those explanations is settled. All of them push the timeline of cosmic chemistry earlier than the textbooks place it. Here is why it matters for the larger story. Cool gas, fast-forming stars, mature disks, central black holes, and dust all link together. A galaxy with a lot of dust cools its gas faster because dust radiates away heat efficiently. Cool gas forms stars faster. Faster star formation produces more supernovae, which produce more dust. The whole cycle can accelerate itself once it gets started. If the early universe started this cycle sooner than expected in some regions, those regions could have run far ahead of the cosmic average, exactly the way Big Wheel did inside its dense environment. The dust problem and the galaxy problem are not separate. They are two ways of measuring the same surprise. The early universe was chemically richer, dynamically more advanced, and structurally more developed than the Standard Model predicted. Each strand of evidence reinforces the others, which raises the heaviest question of all. The Standard Model is not a vague picture. It is a precise framework with specific equations and hard predictions. To understand exactly what is breaking, the model itself has to come into focus next. The model that Webb's discoveries are pressing against has a name: lambda CDM. The lambda stands for the cosmological constant, the term in Einstein's equations that represents dark energy, the force driving the accelerating expansion of the universe. The CDM stands for cold dark matter, the unseen, slow-moving substance that makes up most of the matter in the cosmos. Together, those two ingredients dominate the universe. Ordinary matter, the kind that makes stars and planets and people, is roughly 5% of the total. Dark matter is about 27%. Dark energy is the rest. Lambda CDM is not a casual story. It is a tightly constrained mathematical framework, built from decades of observation. It predicts the temperature pattern of the cosmic microwave background to extraordinary precision. It predicts the way galaxies cluster on large scales. It predicts the abundances of light elements created in the first minutes after the Big Bang. It predicts the expansion history of the universe. Across most of these tests, it has performed almost embarrassingly well. But the model also makes predictions about how fast structure should form. Those predictions are where Webb is putting on the pressure. Cold dark matter clumps slowly. In the model, small clumps form first, then merge into larger ones over time. The largest dark matter cradles, the kind needed to host massive galaxies and clusters, take billions of years to assemble. Inside those cradles, gas falls in, cools, and forms stars at limited rates. The model has parameters for star formation efficiency, gas inflow rates, feedback from supernovae, and feedback from black holes. Those parameters are tuned to match observations of the modern universe. Once they are tuned, they make specific predictions for what the early universe should look like. The predictions are clear. At redshift 10, about 500 million years after the Big Bang, the model expects mostly small, faint, irregular galaxies. At redshift 7, around 800 million years in, slightly larger galaxies, still mostly clumpy, with relatively low total stellar masses. By redshift 3, the model expects galaxies to be approaching modern sizes, but still in active assembly, with mature spirals being rare and unusually massive disks being rarer still. Webb's data does not match those expectations cleanly. There are too many bright galaxies at high redshift. There are too many mature shapes. There are too many supermassive black holes. There are too many heavy elements. There are full clusters that arrived too soon. Each individual observation might be explained within the model with parameter adjustments. The collective pattern is harder to absorb. Astronomers have several responses. The conservative response is to keep the model and adjust the knobs. Maybe early star formation was more efficient than current calibrations assume. Maybe early dust formation was unusually rapid in some regions. Maybe the brightest objects at high redshift, are systematically biased outliers, and the typical early universe still matches predictions. A recent statistical paper from the University of California, Irvine, argued that with careful treatment, most of the apparent tension can be explained without abandoning the model. The more radical response is that the model itself needs revision. Maybe the cosmological constant is not constant. Maybe dark matter is not as cold as we thought. Maybe the early universe had a phase of accelerated structure formation that current models do not capture. A few cosmologists have proposed deeper changes, including modifications to the way distances and ages are calculated across cosmic time. Those proposals are controversial. They are not fringe. Lambda CDM is not falling. It is being squeezed. The squeeze is real. The squeeze is documented. The squeeze is showing up in too many places at once for any single fix to settle it. What kind of fix the universe will demand is the question driving the next round of work. And the next pressure point sits in the rate at which gas turns into stars. Star formation has a speed limit. Inside a galaxy, gas falls inward, cools, fragments into clumps, and those clumps collapse into stars. The whole process is slow because nature pushes back at every stage. Gas heats up when it compresses. Magnetic fields resist collapse. Newborn stars blast radiation outward, blowing nearby gas away. Supernovae explode and clear out whole regions. The galaxy fights itself as it grows. The cap on this back and forth is called star formation efficiency. It is the fraction of available gas that successfully turns into stars before the rest is heated, blown out, or locked away. In the modern universe, that fraction sits around 10 to 20% for typical galaxies. The number is small because feedback is strong. Most gas does not finish the journey from cloud to star. It gets pushed out before it can. Webb's early universe galaxies are forcing astronomers to push that fraction much higher. In some cases, uncomfortably higher. Several Webb candidate galaxies, observed in the first billion years after the Big Bang, carry stellar masses so high that, given the available gas inside their dark matter cradles, the only way to produce them is to convert gas into stars at efficiencies far above modern values. Some early estimates ran above 50%. A few touched or exceeded 100%, which is physically impossible. That ceiling shows up because the math assumes a certain cradle mass tied to standard cosmology. If the cradle is right and the galaxy is real, no remaining gas budget exists to explain the stars. The galaxy used more material than the cradle could provide. That is the efficiency wall. And the wall is what makes the impossible early galaxy problem feel sharper than the gas problem alone. Even if you grant generous gas delivery, you still need physics that lets the gas convert into stars at rates that would shred any modern galaxy. There are ways to climb the wall without breaking the model. Better measurements have pulled some early candidates back into reasonable territory by adjusting their stellar masses downward. Webb sees galaxies indirectly, through their light, and converting light into mass requires assumptions about which kinds of stars are present. Change the assumption set, and the mass changes too. A galaxy assumed to be packed with massive young stars carries a different mass than the same galaxy assumed to be a quieter mix. That recalibration helps. It does not erase the wall, it moves it. A more aggressive idea is the early feedback was weaker than modern feedback. In the very early universe, gas was denser, dust patterns were different, and the galaxies were smaller, so winds and radiation may not have escaped as efficiently. Star formation could have run hotter and longer before being shut down. Some simulations now build this into their early universe runs. They produce more stars, faster. They get closer to matching Webb's data. Closer is not all the way. The most extreme objects still sit at the top of what the simulations can deliver, even with optimistic assumptions about feedback. The galaxies are running ahead of the engines we can model. There is one more layer that pushes the puzzle even further. The wall does not just hit individual galaxies. It hits the cradles they grow inside. If the dark matter cradles in the early universe were exactly the size standard cosmology predicts, even maximum efficiency growth cannot produce the observed populations. The cradles themselves may need to be bigger than the model allows. That is a different kind of problem. Sitting one level deeper in the structure of the cosmos, the cradle question is the next pressure point. A galaxy is the visible part. The cradle around it is invisible. That cradle, made of dark matter, is what holds the galaxy together and dictates how much gas can fall in. Every galaxy you see is sitting inside one. The shape and size of the cradle decide almost everything about the galaxy's potential. In lambda CDM, dark matter cradles grow slowly and predictably. The model gives clear forecasts for how many cradles of each size existed at each cosmic epoch. Massive cradles, the kind needed to host massive galaxies, are rare in the early universe and become more common over time. By 2 billion years after the Big Bang, only a small population of very large cradles is supposed to exist. By 800 million years, those cradles are rarer still. To produce Big Wheel, a cradle in the upper tier of what the model allows had to exist. To produce the largest early supermassive black holes, even larger cradles were needed. To produce El Gordo, a cradle pushed near the absolute cosmic ceiling for its era had to be in place. Webb is showing us several of these objects in different patches of sky at multiple early epochs. The cradles holding them all had to be unusually massive for their time. Either the early universe held more giant cradles than the model predicts, or the same cradles were behaving differently than the model expects. A handful of cosmologists have proposed that the standard prediction for cradle growth may be incomplete. The shape of the dark matter power spectrum, the function that describes how dark matter clumps at different scales, could be slightly steeper at small scales than current measurements suggest. A steeper spectrum would let the largest cradles assemble earlier by feeding them through a richer supply of small predecessors. The change required is not extreme. It is, depending on the version, a few percent in the right direction. But a few percent in the right direction can shift early cradle abundance by a meaningful factor. That kind of change is testable. The cosmic microwave background constrains the power spectrum tightly, but mostly at large scales. Smaller scale measurements are harder. Webb's discoveries may indirectly become a probe of those small scales by showing what kinds of structures the early universe actually built. There are stranger possibilities too. The dark matter itself may not be as cold as the model assumes. Cold dark matter, the standard version, moves slowly and clumps efficiently. Slightly warmer dark matter made of particles with a small thermal velocity would smooth out the smallest clumps. That would actually slow down structure formation, the opposite of what Webb's data needs. Slightly cooler or more interacting dark matter made of particles that clump even more efficiently than standard cold dark matter could do the opposite, accelerating cradle growth in the early universe. Those alternatives are speculative. They are not ruled out. A few astronomers have started talking about the cradle question as the deepest version of the impossible early galaxy problem. The galaxies and black holes are visible, but they are downstream of their invisible cradles. If the cradles are wrong, everything downstream is wrong. If the cradles are right, then something inside them is running on faster physics than expected. Either way, the answer points beneath what we can see directly. That is the strange position cosmology now sits in. The most important variable is invisible. The visible variables are the only way to study it. And those variables are all telling the same story. There may be ways to move the answer without changing the dark matter model at all. Some of those ways involve motion. Galaxies are not just sitting in the cosmic flow, they have their own motions. The expansion of the universe carries them outward, but on top of that expansion, individual galaxies and clusters drift through space at their own speeds. Those local drifts are called peculiar velocities. They are common. They are measured. They are usually treated as a small correction to cosmic expansion calculations. A small group of physicists has argued that in the early universe, peculiar velocities may have been doing more than astronomers usually credit them for. The standard equations describing the expansion of the universe assume a smooth, uniform cosmos at large scales. In that smooth picture, galaxies grow inside cradles whose growth rate is set entirely by the average density of matter and the cosmological constant. Real galaxies, though, do not live in average regions. They live in lumpy ones. Around any given galaxy, the local density is either above or below average, and the surrounding matter is moving with peculiar velocities relative to the cosmic flow. Those local conditions affect how fast the cradle around the galaxy grows. A paper from researchers working in general relativity recently argued that in regions with strong peculiar motions, structure formation could effectively run faster than the smooth cosmos equations predict. The cradle grows quicker. The galaxy inside it grows quicker. The standard model is not violated. It is just being applied to local conditions that the smooth equations average away. This is a quieter solution to the impossible early galaxy problem. It does not require new physics. It does not modify dark matter. It does not change the age of the universe. It just says that the corner of the cosmos where Big Wheel and similar objects live may have had unusually strong peculiar motions, accelerating local structure growth in ways the standard calculations do not capture. The idea is testable. Peculiar velocities leave fingerprints. If the early universe had stronger local flows in dense regions, those flows should appear in the relative motions of galaxies inside those regions. Webb's spectroscopy can measure exactly that. By studying the velocities of galaxies inside Big Wheel's neighborhood, and comparing them to the velocities expected in a smooth cosmos calculation, astronomers can begin to test whether peculiar motions are doing the work the hypothesis credits them with. The early data is suggestive but not conclusive. Some dense early universe regions do show velocity patterns that are richer than smooth predictions allow. Others look standard. The community is collecting more data. The hypothesis remains alive without yet being either proven or rejected. There is a version of this idea that reaches further. If peculiar velocities can accelerate local structure growth meaningfully, then the impossible early galaxy problem may not be a problem with cosmology at large, but with the way we apply cosmology locally. The model may be intact. The application may be too coarse. That is a humbler conclusion than overturning the standard picture, and it is the kind of conclusion that often turns out to be right in physics, even when more dramatic ideas attract more attention. It also does not solve everything. The biggest mass tensions, especially the supermassive black hole masses at very high redshifts, are too extreme to be absorbed by peculiar velocity corrections alone. Even with optimistic local enhancements, the largest early black holes still need new physics in their formation channels. Peculiar velocities can soften the galaxy problem. They cannot dissolve the entire pattern. For that, more aggressive ideas have entered the conversation. Some of them go back nearly a century, only to be revived now under Webb's pressure. The phrase tired light sounds like science fiction. It is, by most accounts, a fringe idea. It has been outside mainstream cosmology for decades. The mainstream consensus is that the redshift of distant galaxies comes from the expansion of space, full stop, and any other explanation has to clear an enormous evidence bar. For most of the 20th century, alternatives could not. Then Webb started returning data that pushed cosmology into uncomfortable territory, and a few researchers reached back into the older toolbox. The tired light idea, in its original form, said that light loses energy as it travels through space, even in a non-expanding universe. The lost energy stretches the wavelength, mimicking the redshift we observe. If true, the redshift would not be a clean record of expansion. It would be a mix of expansion and energy loss. The age of the universe, calculated from redshift, would change. The distances would change. The whole cosmic timeline would have room to flex. Pure tired light models were ruled out long ago because they could not explain the cosmic microwave background well, and they failed to fit the distance versus brightness measurements of distant supernovae. The data closed the door on them. The door is now ajar again, in a specific way. A physicist named Rajendra Gupta, working at Canadian universities, proposed a hybrid model that combines a tired light component with the standard expanding universe. In this hybrid, redshift comes mostly from expansion, but a small additional contribution comes from tired light energy loss. The hybrid, when calibrated against multiple datasets, can in some versions stretch the calculated age of the universe to nearly 27 billion years. That is roughly twice the standard figure. Inside that doubled timeline, the impossible early galaxy problem softens dramatically. A galaxy at redshift 3.25, which the standard model places about 2 billion years after the Big Bang, would in this model sit at roughly 6 billion years. Big Wheel would have had several times longer to grow. Its mature spiral structure would no longer be impossible. It would be ordinary. The proposal is controversial. Most cosmologists reject it. It conflicts with multiple precisely measured cosmic parameters, especially those tied to the cosmic microwave background. Its hybrid version has more free parameters than the standard model, which makes it easier to fit observations, but weaker as a theory. It has not gained traction in the broader community. Gupta has continued to publish, refining the model. Other researchers have explored related ideas, including modifications to the way fundamental constants behave across cosmic time. Most of these proposals share a goal: buy the universe more time. Let the early structures grow without forcing changes to dark matter or seed black holes. Stretch the clock instead of redesigning the physics. Webb has not validated any of these proposals. It has put pressure on the mainstream model that makes such proposals interesting again, even to skeptics. In the scientific process, ideas that were dismissed 20 years ago can become worth re-examining when new data arrives, not because the old ideas were right, but because they sit in the conceptual space that needs new thinking now. That is what tired light, in its modern hybrid form, has become. A signal. A reminder that the assumptions buried inside cosmology can be revisited if the data demands it. Most of those assumptions will hold up. A few may not. The tools we are using to test them are sharper than ever, and the testing is only beginning. The next idea on the list goes deeper than the redshift itself. It reaches into the constants of nature. The constants of physics are supposed to be exactly that. Constant. The speed of light. The gravitational constant. The fine structure constant that governs electromagnetism. These numbers appear in every equation. Every measurement we make, every theory we build, assumes they have always been the same. What if they have not been? The covariant constants proposal, developed by Gupta and collaborators, suggests that several fundamental constants may evolve together over cosmic time, each one changing in a coordinated way that preserves the laws of physics as we know them locally, but stretches the cosmic timeline globally. The idea is mathematically more disciplined than it first sounds. The constants are not changing freely. They are tied to each other in specific relationships, and the changes cancel out in most local measurements, which is why we have not noticed them. In this framework, the cosmic distance versus time relationship shifts. Light from distant objects has traveled through a universe whose effective parameters were slightly different in the past. The redshift we measure picks up an extra component from this evolution, beyond pure expansion. Calculated cosmic ages stretch out. By the proposal's calibration, The universe could be roughly 27 billion years old, with corresponding extensions of the time available at every redshift. Inside this extended timeline, the impossible early galaxy problem largely vanishes. Big Wheel has had time. The supermassive early black holes have had time. El Gordo has had time. The dust has had time. The clock that current cosmology says is too short becomes long enough. Most cosmologists are skeptical. The proposal makes specific predictions for several observables, and not all of them match standard data well. The cosmic microwave background, in particular, sets tight constraints that are hard to satisfy with any model where fundamental constants drift significantly. Gupta's papers have proposed adjustments that try to thread this needle, but the threading is technical, and the community has not been broadly convinced. The ideas keep being published, though. They keep being cited. They keep coming up at conferences. That is the marker of a proposal that has not been accepted, but has not been killed either. It sits in the active, speculative tier of cosmology, alongside other non-standard models that are taken seriously without being adopted. There is something philosophically interesting about this kind of idea. It raises a question that physics has had to confront before. How sure are we that the constants of nature have always been what they are now? The answer in mainstream physics is that we have many measurements showing they do not vary at the precision we can test. Those measurements are local, recent, and limited in their reach across cosmic time. Beyond a certain depth, our certainty drops. We trust extrapolation. The extrapolation might be wrong. Webb is a tool that can begin to test it. By measuring properties of distant galaxies and comparing them precisely to local equivalents, astronomers can probe whether physical processes operated identically in the early universe. So far, most measurements are consistent with unchanging constants. The consistency is not absolute. Some papers have reported small hints of variation in particular parameters, including the fine structure constant, in the spectra of very distant quasars. The hints are at the edge of measurement noise. They may be real. They may be artifacts. Whatever the answer turns out to be, the mere fact that these ideas are now being published in mainstream journals and discussed at major conferences shows the size of the disturbance Webb has introduced. The impossible early galaxy problem has reached the level of nudging cosmologists to question constants they previously treated as off-limits. The next idea is even older than tired light, and it sits closer to direct observation. The standard picture says stars came first, and stars made the first black holes. That is the slow seed channel. The fast seed channel involves direct collapse, where gas collapses into a heavy black hole without first making stars. There is a third channel, even more aggressive, that some cosmologists have been thinking about for decades: primordial black holes. The idea is that black holes formed in the first fractions of a second after the Big Bang, not from collapsed stars or collapsed gas, but from extreme density fluctuations in the early plasma itself. If the universe right after the Big Bang had the right kind of inhomogeneities, regions denser than their surroundings would have collapsed directly into black holes, with masses determined by the size of the collapsing region. Some primordial black holes might be tiny, evaporating long ago through Hawking radiation. Others might be heavy, persisting to the present, growing across cosmic time. If primordial black holes exist, they would have been around long before the first stars. They would have served as ready-made seeds for galaxy formation, sitting at the centers of forming dark matter cradles, pulling in gas from the moment it became available. Some of the earliest supermassive black holes that Webb is now seeing might trace their origins to primordial seeds, not to collapsed stars or direct collapse clouds. That would solve the timing problem cleanly. A primordial black hole with a few thousand solar masses, formed in the first second after the Big Bang, could grow into a supermassive black hole within the available cosmic time. It would not need a head start from rare conditions. It would have been there from the beginning. The idea is not new. It dates back to the 1970s. For most of its history, it has been a fringe possibility. It has not been confirmed. It has not been ruled out. The observational constraints on primordial black holes are tight in some mass ranges and loose in others. Black holes around the mass needed to seed early supermassive black holes happen to sit in a relatively unconstrained zone. Webb's discoveries have revived interest. A few papers in the last 2 years have argued that primordial black holes provide the cleanest explanation for the largest early black holes, simpler than direct collapse and more flexible than super Eddington feeding. The argument is not that we have positive evidence for them. The argument is that they fit the data better than the alternatives, and they should be taken seriously as a possibility while better data accumulates. There are observational handles. If primordial black holes exist in significant numbers, they should affect the cosmic microwave background through their gravitational influence on early plasma. They should influence the way galaxies cluster on small scales. They should produce gravitational wave signals when they merge, detectable by current and future observatories. None of these signals has been definitively detected. None has been definitively ruled out either. This is the kind of idea that lives in the gap between speculation and possibility. It cannot be confirmed without specific evidence. It cannot be dismissed without evidence either. The pressure from Webb has moved it from the back of cosmology's filing cabinet into the active drawer. Whether it stays there depends on what the next decade of observations show. If primordial black holes existed, the early universe was even busier than Webb is currently showing us. Hidden engines, formed before stars, would have been pulling in gas, growing into supermassive monsters, and shaping the structures around them, all while the cosmos was still in its first chapter. The galaxies we now see may be late arrivals to a story that began before any star ever shined. The first stars themselves have a role to play in this. They may have run faster than expected too. The first stars in the universe never had a name in their own time, because there was nobody to name them. Astronomers called them Population 3. They were the original stars, born from the primordial mixture of hydrogen and helium, with virtually no heavier elements to work with. They lived briefly. They died spectacularly. None of them survives today because they all burned through their fuel and exploded long ago. We have never directly observed a population 3 star. They are inferred from theory and from the chemical fingerprints they left in later generations. The standard picture, built from simulations, says population 3 stars were unusually massive, sometimes hundreds of times the mass of our home star. They lived for only a few million years before exploding as supernovae, scattering the first heavy elements into the surrounding gas. They were the universe's first chemists, and the seeds of everything that came after. Webb is now in a position to maybe see the last of them, or more likely, see their immediate descendants and pick up indirect signatures of their existence. Some early universe galaxies show light patterns that could be consistent with hosting population 3 stars in small clusters near their cores. The detections are tentative. The community is cautious. Confirming a true population 3 observation would be one of the most significant discoveries in the history of astronomy, and the bar is appropriately high. The reason population 3 matters for the impossible early galaxy story is timing. If population 3 stars formed earlier than expected, lived more massively than expected, or died more violently than expected, they would have seeded the early universe with heavy elements faster than the standard story predicts. That seeding is the prerequisite for nearly everything else. Cool gas needs heavy elements to radiate energy efficiently. Star formation in subsequent generations runs faster when those heavy elements are present. Dust grain formation needs them. Black hole feeding through dense gas envelopes needs them. A faster population 3 phase would compress the timeline of all the subsequent surprises. Early dust enrichment would follow naturally. Faster star formation in second-generation galaxies would follow. Heavier early black hole seeds formed inside the unusually dense cores of population 3 environments would follow. The whole pattern that Webb is now seeing could trace back to a population 3 phase that ran hotter and faster than the standard models assume. There are theoretical reasons to think this might be the case. Population 3 star formation depends sensitively on the cooling properties of primordial gas, and those properties depend on conditions we cannot directly measure. Small adjustments to assumed conditions can change predicted population 3 masses, lifetimes, and spatial distributions significantly. Some recent simulations, run with updated cooling models, produce population 3 populations that are more concentrated and more impactful than older simulations predicted. A particularly aggressive version of this idea proposes that the very first stars were not powered by ordinary nuclear fusion at all. They were dark stars, supported against gravity by dark matter annihilation in their cores, before transitioning to standard fusion. Dark stars, if they existed, could have been even more massive than standard population 3 stars, lasting longer, accumulating more mass, and ending their lives in even more dramatic ways. The Webb team has reported a few high redshift sources whose spectra are at least consistent with the dark star idea. Those reports are not confirmations. They are intriguing data points being studied carefully. Whatever the truth turns out to be, population 3 is likely a piece of the impossible early galaxy puzzle. The first stars set the pace for everything that followed. If they set it faster than we thought, the rest of the pattern starts to make sense. The instrument seeing all of this is itself part of the story. Without Webb, almost none of these tensions would be visible at all. Hubble launched in 1990. For more than 3 decades, it gave humanity its clearest views of the deep universe. It found galaxies billions of light years away. It traced the expansion rate of the cosmos. It studied dust in nearby spirals, atmospheres of nearby planets, and gravitational lensing in distant clusters. Hubble was, by almost any measure, the most successful scientific instrument ever built. Hubble could not have found Big Wheel. It could not have resolved the little red dots. It could not have confirmed Alexander's spiral structure. The reason is simple. Hubble sees primarily in visible and ultraviolet light. The most distant galaxies in the universe have had their light stretched so far by cosmic expansion that by the time it reaches us, it has shifted into the infrared. Visible light telescopes cannot see them clearly. Infrared telescopes can. Webb is an infrared instrument. It was designed from the ground up for exactly this purpose. Its mirror is 6.5 meters across, roughly 2.5 times the diameter of Hubble's. Its detectors are tuned to wavelengths that Hubble could barely sense. It sits at a stable point in space about 1 million miles from Earth, far enough from our planet's heat that its instruments stay extraordinarily cold, which is essential for sensitive infrared measurements. That combination of size, location, and detector design gives Webb capabilities that no previous telescope had. It can detect galaxies whose light has been redshifted into the deep infrared. It can resolve their shapes. It can measure their spectra precisely enough to nail down their distances. It can distinguish a mature spiral from a young clump, a black hole from a star cluster, a dust-rich galaxy from a dust-poor one. Almost every surprise in the impossible early galaxy story depends on at least one of those capabilities. Big Wheel's spiral structure required spatial resolution. Its rotation curve required spectroscopic sensitivity. The little red dots required infrared sensitivity at faint flux levels. Heavy element abundances in early galaxies required spectra that Hubble could not deliver. The pattern of impossible-seeming objects only became visible because the instrument made it visible. This is worth pausing on. Cosmology has always been limited by its tools. The history of the field is the history of new instruments, revealing new facts that overturn old assumptions. The cosmic microwave background was discovered when radio telescopes became sensitive enough to detect it. The accelerating expansion of the universe was discovered when supernova surveys became precise enough to map it. Dark matter, dark energy, the ages of the oldest stars, the abundances of light elements, all of these came into focus through specific instruments that could measure what their predecessors could not. Webb is the latest in that line. It has revealed an early universe that is more complex, more developed, and more puzzling than its predecessors suggested. The complexity was probably always there. We just could not see it. That is a humbling thought. The universe does not change to match our instruments. Our instruments change to match the universe. Each upgrade reveals what was already happening, hidden from us by the limitations of what we could measure. There is a counterpoint, though, and it deserves serious weight. New instruments can also produce new biases. Webb sees the brightest, most concentrated, most active early galaxies more easily than the faint, diffuse, ordinary ones. The pattern Webb is showing us may not be the typical pattern of the early universe. It may be the bright tail of a much larger distribution, most of which we still cannot see well. That counterpoint shapes the next chapter of the debate. Every survey has a bias. The universe contains far more galaxies than any telescope can study, and the ones that get studied are the ones bright enough, large enough, or otherwise prominent enough to pass the survey's detection threshold. That threshold is real. It cuts off everything below a certain brightness, no matter how interesting it might be. The galaxies we know about are the ones above the cut. Selection bias matters for the impossible early galaxy problem, because it changes the meaning of the pattern. If Webb is finding mature massive galaxies in the early universe, that fact alone does not tell us that mature massive galaxies were common back then. It tells us that they existed in some numbers, and that the brightest ones rose above Webb's detection threshold. Below that threshold, there could be vast populations of ordinary, small, faint, slow-growing galaxies that match the standard model perfectly. We just cannot see them. This is the conservative response to the tension. The standard model predicts a distribution of galaxies. Most of them are small. A few are large. The largest sit at the rare top end of the distribution. If Webb is seeing only the top end, it might be telling us about the top end without telling us anything is wrong with the bulk. Recent statistical analyses have made this case carefully. A paper out of the University of California, Irvine, published last year, argued that when you account for measurement uncertainties, modeling systematics, and the natural rare end of the predicted galaxy distribution, most of the apparent tension between Webb's data and lambda c dm dissolves. The galaxies are unusual, but unusual is allowed by the model. Outliers exist. Outliers should exist. Finding outliers does not break the model, unless they are far more common than the rare tail allows. This argument has weight. It is not a dismissal. It is a careful read of the statistics. And statistics in cosmology are notoriously subtle. The early Webb papers that claimed the most extreme efficiencies often had the largest measurement uncertainties. Better follow-up observations have, in many cases, pulled those galaxies back into less extreme territory. The headlines may have been louder than the underlying physics. There are limits to how far this argument can stretch. Some of the early universe surprises are not just brightness outliers, they are structural surprises. Big Wheel's spiral form is not a feature of brightness. It is a feature of dynamical maturity. Mature spirals were not predicted to exist at that epoch in any significant number, no matter how rare. The Tully-Fisher relation that Big Wheel sits on is not a measurement that can be massaged by recalibration. The galaxy is dynamically what it appears to be. The little red dots, similarly, are not just bright outliers. They form a distinct population with consistent properties. If they are direct collapse seeds or black hole stars, their existence in numbers tells us something about early universe physics that the standard model does not naturally predict. The honest read on selection bias is that it matters and it does not solve everything. It softens the most extreme tensions. It pulls the galaxy mass anomaly toward less alarming territory. It cannot dissolve the structural anomalies, the black hole mass anomalies, or the consistent pattern across multiple object classes. Astronomy, as a field, is now sitting with both responses simultaneously. The conservative response says the model holds with adjustments. The radical response says the model needs revision. The data is consistent with both, depending on which observations you weight most heavily. That is an unstable equilibrium. The next round of observations will tip it. Beyond selection bias, there is a broader category of arguments that defend the standard model. They go under the name systematics. A systematic, in the language of physics, is any measurement effect that is not purely random, that introduces a consistent bias into your data. Systematics are everywhere in observational astronomy. They are the boring, painful, technical issues that often determine whether a result is real or an illusion. The defense of lambda CDM rests heavily on systematics. The argument goes like this: Webb is a new instrument. New instruments have new systematics that take time to understand. The first generation of papers using a new telescope often overstates results because the systematics have not been fully calibrated. Galaxy mass measurements, in particular, depend on assumptions about stellar populations, dust extinction, redshift accuracy, and many other parameters. Each of those assumptions has its own systematic uncertainty. Stack them together, and the resulting mass measurement has a wider uncertainty than any single paper can quantify. When you combine larger uncertainties with the natural variability of cosmological objects, the apparent tension softens. A galaxy whose central estimate is far above what the model predicts, but whose true mass could plausibly be a factor of 2 lower, may not actually be a problem for the model. Several Webb candidates have already been revised downward in mass through better measurements. The pattern of revisions is consistent. As more data accumulates, many extreme cases become less extreme. This defense has substance. It is the right kind of skepticism for a young field. Cosmology has been burned before by early results that did not survive better measurements. The history of the Hubble constant, the rate at which the universe expands, includes decades of measurements that argued with each other before settling. The history of dark matter measurements includes early estimates that turned out to be wrong by factors of 2 or more. Patience and replication are how the field arrives at truth. There is an argument about specific objects too. Some early Webb candidates were originally claimed at very high redshifts, but turned out, on closer examination, to be lower redshift objects with unusual spectral features. The number of confirmed extreme cases is smaller than the number of initial claims. That is normal in observational astronomy. It does not mean the early claims were dishonest. It means the early data was thin, and the thin data was overinterpreted. Where the defense weakens is in the structural and dynamical findings. Big Wheel's redshift is robust, its spiral structure is visible, its rotation curve sits where it sits. The little red dots' compactness and color are robust across multiple analyses. El Gordo's mass is large, with calibration uncertainties that do not bring it back into ordinary territory. The supermassive black hole masses at the highest redshifts have been measured by multiple teams using multiple methods, and the central values do not move much with better analysis. The honest position, which most working cosmologists hold, is that the systematics defense has eaten some of the tension and cannot eat all of it. The model is in trouble in specific ways, in specific corners of the data, that are not reducible to measurement noise. The trouble may turn out to require new physics. It may turn out to require revised parameter values within existing physics. It may turn out to require better understanding of complex environments where average equations break down. What it will not turn out to require is panic. Cosmology has always advanced through tension. Tensions push the field. The current tensions are pushing it now. The push is real. The collapse is not. That brings the question to where the evidence actually stands today. It helps, at this stage, to separate what is settled from what is still in motion. Confirmed. Big Wheel exists. Its redshift, its size, its rotation, and its mass are measured by multiple methods and published in peer-reviewed work. Alakananda exists, with its grand design spiral structure and its early epoch confirmed. Multiple supermassive black holes exist at very high redshifts, with masses far above what stellar remnant seeds could produce on the available timeline. El Gordo exists, with its enormous mass and high-speed collision dynamics. The little red dots exist as a distinct population with consistent observational properties. Heavy elements are present in the early universe at levels that imply faster chemical evolution than the standard story allows. Contested. The interpretation of the little red dots as direct collapse black hole seeds, also called black hole stars, is gaining ground but not settled. Some teams favor a starburst interpretation, others favor the active black hole interpretation, and the community has not converged. The exact stellar masses of the most extreme early galaxies are contested, with some candidates being revised downward as better data accumulates. The role of feedback in early galaxies is contested, with different simulations producing different results depending on assumed parameters. The probability of producing observed objects in standard cosmology is contested, with statistical analyses arriving at different conclusions depending on methodology, unknown. We do not know whether the standard cosmological model needs new physics, parameter adjustments, or simply better statistical treatment. We do not know whether the most extreme early black holes form from direct collapse, primordial seeds, super Eddington feeding, or some combination. We do not know whether the patterns Webb is finding extend into the bulk of the early galaxy population, or sit only at the bright tail. We do not know whether peculiar velocities, dark matter, halo modifications, or extended cosmic timelines provide the answer. We do not know whether the constants of nature have varied across cosmic time. We do not know what fraction of the impossible early galaxy problem is observational selection, and what fraction is genuine physics. That is the honest map. Confirmed at the outer edges, contested in the interpretive middle, unknown at the deepest level. Astronomy lives with maps like this all the time. Most major fields in physics have similar maps right now. The field of cosmology is unusually sensitive to data because there is only one universe to observe, and we cannot run experiments on it. We can only watch it carefully and reason backward from what we see. What can be said with confidence is that Webb has changed the landscape. It has not overturned cosmology, it has not falsified the Big Bang, it has not proven any alternative theory. It has, however, moved the boundary between settled and unsettled. Things that were treated as settled 5 years ago, like the rate at which structure formed in the early universe, are now treated as open questions. Things that were treated as fringe, like primordial black holes and modified cosmology proposals, are now discussed at major conferences and published in mainstream journals. That kind of shift does not happen often in physics. It happens when new data demands it. The data is demanding it now. What the early universe actually looked like is, as a result, being redrawn in real time. The old picture had a slow start, a long assembly phase, and a gradual emergence of structure. The new picture is busier, faster, and richer, at least in some regions. Webb is showing us a cosmos that had more going on sooner than the old textbook said. The shape of that cosmos is starting to come into focus. Imagine the early universe as an empty dance floor. The standard model says the first dancers were small, tentative, scattered. Over time, they found partners, formed groups, and eventually built the elaborate choreography we see today. The early floor was sparse and clumsy. The modern floor is intricate. Webb is showing us a different early floor. In some regions, full dances are already underway by the time the music has barely started. Mature spirals turning gracefully. Massive partnerships already locked in. Black holes at the center of the floor, pulling whole crowds inward. Dust and chemistry already painting the air. The dance is not just starting. In privileged corners of the floor, it has already advanced. That changes how we should picture the early universe. It was not a uniformly slow start. It was patchy. Most of the floor was indeed sparse and tentative, matching the textbook picture. A minority of regions ran far ahead, hosting structures that the bulk of the cosmos would not produce for billions of years more. Webb is sensitive enough to see those advanced regions for the first time, and what it sees there is reshaping the broader picture. This patchiness has consequences. It means the early universe was a place of strong contrasts. Some regions were quiet, with small forming galaxies and shallow cradles, slowly collecting gas. Other regions were violent, with multiple mergers, intense star formation, feeding black holes, and dense filamentary inflows. The contrast between these regions was probably greater than the modern universe shows. Today, most galaxies live in environments somewhere in the middle of the density distribution. In the early universe, the extremes were more extreme. The dense regions were denser relative to the cosmic average than they are now. That has implications for almost everything we want to learn about the early universe. The first generations of stars probably formed preferentially in the dense regions, where gas could cool and clump quickly. The first black holes probably grew in those same regions, fed by the same dense gas. The first heavy element enrichment happened there. The first dust formation happened there. The first structural maturity happened there. The privileged regions were where the universe wrote its first chapters, and the rest of the cosmos slowly caught up over billions of years. Big Wheel is one of those first chapters, frozen in light, finally readable. There is a deeper layer to this picture. If the early universe was patchy, then averaged measurements of the early universe miss what the patchiness was actually doing. The cosmic microwave background, our best measurement of the very early cosmos, gives us an average. It tells us the universe at 380,000 years after the Big Bang was almost perfectly uniform, with tiny temperature fluctuations of 1 part in 100,000. Those tiny fluctuations grew under gravity into the structures we see today. The growth happened differently in different regions, depending on local conditions. The differences compounded over time. Webb is showing us how dramatically they compounded. Some cosmologists are now arguing that the simple, smooth universe equations, which work beautifully on average, miss important effects when applied to the most extreme regions. The growth of structure in dense, privileged regions may have proceeded differently than the smooth equations predict. The corrections are subtle, but at extreme densities, they may add up to meaningful differences. The peculiar velocity argument mentioned earlier is one example of this kind of correction. Whatever the technical resolution, the observational picture is clear. The dawn of the universe was busier than we thought. Faster, richer, more contrasting, more productive of structure in some places, while the rest caught up. That picture has consequences for our own galaxy, and for the story of where we came from. The Milky Way is roughly 13 billion years old. Its central black hole, with about 4 million solar masses, is modest by cosmic standards. Its stellar mass is something like 50 to 100 billion times the mass of our home star. Its disk is mature, with 2 main spiral arms and several smaller ones. Its dark matter cradle holds it all together. We have always told the Milky Way's story as a slow, gradual one. The galaxy assembled over most of cosmic time. Mergers built it up. Gas inflow fed it steadily. Black hole growth was slow. Disk formation was a late development. The whole arc was supposed to take 10 or 11 billion years to reach its current state. Webb's discoveries do not necessarily change the Milky Way's story. They do change the context. They show us that the rate at which our galaxy assembled was not the only available rate. Some galaxies, in privileged environments, reached Milky Way-like states billions of years sooner. We were not on the fast track. We were on the ordinary one. Our environment was not a dense, accelerated corner of the early universe. It was a typical region, with typical inflow, typical mergers, typical pace. That shifts the meaning of our own galaxy. The Milky Way is not the universe's standard outcome. It is one outcome among many, shaped by the conditions of the region it grew in. Other galaxies in other regions grew faster, larger, or with different structures. Some grew slower or smaller. The diversity of outcomes is greater than the standard story implied. There are practical implications. If the Milky Way's history is more typical than exceptional, then the question of why life arose here becomes slightly easier to ask. We did not need a privileged early universe environment. We needed a stable, ordinary disk galaxy with enough heavy elements to make rocky planets and enough quiet time for those planets to develop atmospheres. Those conditions probably existed in many galaxies, not just the most exceptional ones. The galactic environment that produced Earth is more likely to be replicated elsewhere than the big wheel-style accelerated environment is. There is also a question about our central black hole. The Milky Way's central engine is small compared to the supermassive black holes Webb is finding in the early universe. Some of those early black holes are tens of thousands of times more massive than ours, despite being seen at much earlier cosmic epochs. That comparison forces a question. Why did our galaxy not produce a larger central black hole? The likely answer is that we did not live in a privileged early region. The conditions for forming heavy seed black holes did not develop in our cradle. We grew on the slow path, with a stellar remnant seed that grew gradually over billions of years. That is a small consolation. A galaxy with a quieter central engine is, in many ways, a better place for life. Active galactic nuclei radiate powerfully across their host galaxies, and life close to a feeding supermassive black hole has to contend with intense radiation. The Milky Way's modest central engine, in this view, is part of why Earth has been able to develop and sustain life across billions of years. The exceptional galaxies of the early universe are spectacular, but they are not necessarily good homes. Webb's discoveries, in this sense, deepen our understanding of where we fit. We are an ordinary galaxy in an ordinary region, doing ordinary things on an ordinary timeline. That ordinariness, far from being a disappointment, may be exactly what made everything that followed possible. The bigger story, though, is not about us. It is about the engines at the center of those exceptional galaxies, and the search for where they came from. The first black holes are one of the great mysteries of cosmology. We know they existed. We see their descendants in every massive galaxy today. We see their early forms as quasars at the edge of the visible universe. We do not know how they got started. The search for the first black holes has been a slow, technical effort for decades. Theorists have proposed multiple seeding channels, stellar remnant seeds formed from the deaths of the first stars, direct collapse seeds formed from primordial gas clouds without first making stars, primordial seeds formed in the first second after the Big Bang. Each channel makes different predictions about the masses, distributions, and growth histories of the resulting black holes. Each channel has implications for what we should observe in the early universe. Webb is now in a position to test these predictions in ways that were not possible before. Its sensitivity to faint, distant objects, combined with its spectroscopic precision, lets it probe the population of early black holes across a much wider range of masses than previous instruments could. The little red dots, if they are early feeding direct collapse seeds, are direct evidence for the heavy seed channel. The supermassive black holes at the highest redshifts, with masses too large for stellar remnant seeds to explain, are also evidence for non-stellar seeding. The picture emerging is that multiple seeding channels probably operated in the early universe. Not all early black holes start the same way. Some started small, from collapsed stars. Some started medium, from direct collapsed clouds. Some possibly started even bigger, from primordial seeds present from the beginning. Different early environments favored different channels. Dense regions probably hosted more direct collapse seeds. Quieter regions probably relied more on stellar remnant seeds. Primordial seeds, if they existed, would have been distributed across both. That is a more complicated picture than the standard story used to hold. The standard story emphasized stellar remnant seeds and treated direct collapse as a special case. Webb is suggesting that direct collapse may have been more common, and primordial seeding may have to be taken seriously as an alternative. The implications run beyond the early universe. Modern supermassive black holes carry the legacy of their seeding history. A galaxy whose central black hole came from a direct collapse seed should have a slightly different mass-to-galaxy relationship than one whose seed came from a stellar remnant. The modern relationship between black hole mass and galaxy mass, called the M-sigma relation, may carry fingerprints of multiple seeding channels mixing together over cosmic time. Webb has only started this work. The observations needed to fully test seeding channels require larger samples, longer integration times, and better spectroscopic data than have been collected so far. The next several years of Webb operations will produce that data. Other telescopes, including future infrared observatories and gravitational wave detectors, will add complementary information. By the early 2030s, the picture should be much clearer. The story has a quiet elegance to it. The first black holes were the seeds from which the modern universe grew. Their descendants now sit at the center of every major galaxy, including ours. They shaped the way galaxies formed, fed, and grew. They influenced star formation in their host galaxies through feedback. They are connected, through long chains of influence, to the conditions that allowed life to emerge in galaxies like the Milky Way. We are, in a real sense, the descendants of choices the universe made in its first hundreds of millions of years. Webb is showing us what those choices were, in regions where they were made most dramatically. The same kinds of choices, in quieter forms, shaped the conditions that led to us. The next observations are about turning the dramatic into the systematic. Webb's first 3 years of operations have been a period of discovery. The next several years will be a period of systematic study. The instrument's operators are now using it not just to find new objects, but to build a comprehensive map of the early universe's structure formation, mapping galaxies, black holes, and gas across a wide range of redshifts and environments. Several major surveys are underway or planned. They aim to answer specific questions raised by the first round of discoveries. How common are mature spirals like Big Wheel in the early universe? How rare or how typical are objects of that kind? Are they confined to dense environments? Or do they occasionally appear in average regions too? What fraction of the early universe's galaxy population was already structurally mature, and what fraction was still in the chaotic assembly phase? Other surveys focus on the little red dots. How many of them exist across different redshifts? Do they evolve in observable ways? Are their spectra consistent with direct collapse seeds, with starburst galaxies, or with some mixture? Do they correlate with the locations of later stage active black holes, suggesting evolutionary continuity? Black hole surveys aim to measure the masses, distributions, and feeding rates of supermassive black holes across the early universe systematically. Are the most massive early black holes confined to the densest regions, or are they distributed more uniformly? Do their host galaxies match what we would expect from the standard mass relation, or do they deviate in informative ways? What is the typical Eddington ratio of feeding in the early universe, and does it support super Eddington phases? Surveys of metal abundances and dust content map chemical evolution across cosmic time. When did heavy elements first become widespread? Which early galaxies show the most extreme enrichment? And what does that tell us about population 3 star formation? How does the dust-to-gas ratio evolve across redshift? Each of these surveys produces data that, combined, will narrow the impossible early galaxy problem. Some scenarios will be ruled out, others will be reinforced. The current speculative landscape, with multiple competing explanations all alive, will likely shrink as the data accumulates. There are also targeted observations of specific objects. Big Wheel itself is being studied in greater depth. Higher resolution spectra of its arms and bulge can tell us about the ages of stars across the disk, helping reconstruct its formation history. Similar studies are planned for Alaknanda. Many of the high redshift supermassive black holes are being followed up with deeper spectroscopy to refine mass measurements and search for outflow signatures. Webb is not the only instrument involved. Other observatories complement it. The Atacama Large Millimeter Array, sensitive to cool gas and dust at very long wavelengths, can study the gas content of early galaxies in detail. The Chandra X-ray Observatory continues to study supermassive black holes through their X-ray emission. The future Vera Rubin Observatory, scheduled for first light, will produce the largest sky survey in history, finding rare early universe objects at scales no instrument has done before. By the end of this decade, the impossible early galaxy problem should look very different than it does today. Some current tensions will probably resolve. New tensions will probably appear. The shape of the answer is impossible to predict in advance, because the answer depends on what the data actually shows. That is the nature of empirical science. The questions the field is asking now will be replaced by sharper questions in a few years. What is unlikely to change is the basic shift in how we think about the early universe. The pre-Webb picture is gone. The post-Webb picture is still being drawn. Whatever the details turn out to be, the new picture will be richer, busier, and more surprising than the one it replaced. The deepest question, though, sits beyond any single observation. There are two ways to read the impossible early galaxy story. The first reading is technical. The standard model needs adjustments. Star formation efficiency was higher than current calibrations assume. Dark matter cradle growth had wider tails than current statistics capture. Selection bias accounts for some of the apparent excess. The model survives, slightly modified, with new parameters tuned to match Webb's data. The second reading is bigger. The standard model is missing something fundamental about how the early universe worked. Some piece of physics we have not yet identified accelerated structure formation in the first billion years. The piece may be related to dark matter, dark energy, primordial black holes, modified gravity, or something stranger. Whatever it is, it operated mostly in the early universe, where the conditions were extreme, and it became less important as the cosmos aged. That is why we did not notice it before. We were measuring a universe in which the missing physics had already faded into the background. Both readings are alive in the field today. The first is more conservative and more likely. The second is more dramatic and less likely, but not negligibly so. The probability the field assigns to each will shift as more data comes in. There is a third possibility, quieter and harder to test. The pieces of the standard model might be right, but the way we have been combining them might be too simple. Real cosmological structure formation involves complex interactions between gravity, gas dynamics, radiation, magnetic fields, and feedback processes that we cannot fully simulate at the resolution needed. The simulations that produce the standard predictions average over many of these complexities. The average predictions miss specific behaviors that emerge only at high resolution in extreme environments. Webb may be showing us those specific behaviors, which the simulations cannot yet reproduce, even though the underlying physics is correct. In this third reading, no new physics is needed. What is needed is better simulations, better calibration of feedback processes, and a better understanding of how matter and energy actually flow in the densest early environments. The model survives, and the apparent tension dissolves into our own modeling limitations rather than into reality. That is a humbler conclusion. It is also one of the most likely. Science often turns out, in retrospect, to have been confused not by reality but by our own simplifications of reality. What does any of this mean for someone who is not a cosmologist? The honest answer is that it is one of those rare moments when the scientific community is genuinely uncertain about something fundamental, and the uncertainty is being acknowledged in real time. Most scientific revolutions look obvious in retrospect, and were invisible to most observers while they were happening. The current moment is unusual in that the tension is visible while it is being worked out. Anyone watching can see it. The first chapter of the universe is being rewritten. Not necessarily in dramatic ways, possibly only in small but important ones. The headline does not need to be that the Big Bang is wrong. The Big Bang is not wrong. The headline is that the first billion years of cosmic history were busier, faster, and stranger than the textbook suggested, and that the simple, slow assembly picture has reached the end of its useful life. What replaces it will be richer. Some of it will be familiar. Some of it will be genuinely new, The pieces are being assembled now by thousands of astronomers working on Webb data, on follow-up observations from other telescopes, on new simulations, on theoretical proposals. The structure that was not supposed to be there has done its work. It has cracked the door open. What walks through it next is the next chapter of cosmology, written by the universe itself in a language we are still learning to read.